Welcome back to ECE 501B. Your homework number 2 is due today. Homework number 3 is not due in a week. It's due a week and a Monday from now. And exam number 1 is due in 2 weeks. Well, will occur in 2 weeks, not due. It will be due in 2 weeks. You will have it in 2 weeks. Today what I want to do is do something like what we did last time with null spaces. Now we'll talk about range spaces. With null spaces, we were dealing with the input vector space, and when does it produce vectors that go to the 0 vector. Now we are worrying about where can we get to in the output vector space. What's the range? And so we'll just state the definition and state that it's a subspace, and then we will talk about a surjective map, which is connected with the range. That's why I've underlined the R's. The surjective map is an onto map. The injective map was a one-to-one map. So we can have maps that are both injective and surjective, neither, or one or the other. And we have all those different combinations. Then we'll look at illustrating that with an example of null space and range space. That will lead us, I hope, to thinking about a relationship between these numbers concerning the input vector space dimension. The dimension of the input vector space, which is V, is actually equal to the dimension of the null space of this linear operator plus the dimension of the range space. And keep in mind that the range space is in what vector space? W. So even though it's in W, its dimension plus the dimension of the null space of T, that's in the vector space V. The sum of those gives us the dimension of V. And we'll try to prove that. Then there are corollaries dealing with injective maps and surjective maps and dimensions. And if we get that far, we'll talk about matrix representations of linear maps. And then we'll talk about maps that are indeed injective, one-to-one, and onto surjective, which means that they are invertible. And then we'll talk about isomorphic vector spaces, which really means that those vector spaces are similar in terms of the way that they behave or their properties. Here's the description of range. The range of a linear map, and this is going from an input vector space V to an output vector space W. This is now the set of vectors in the output vector space W, which are obtained after passing through the linear map. Where can we get to if we simply maybe randomly start selecting V's from our input vector space and pushing those through or mapping those through T? And that gives us this picture, which is coming up out of the bottom. But our input vector space is on the left. We're picking V's, but I'm trying to emphasize the fact that R of T may not fill the cloud, where the cloud is the output vector space W. What I'm trying to suggest here is the range of this linear map may not be all of the output vector space W. That's pictorially what I'm trying to illustrate by that red cloud being a little bit smaller than the enclosing black cloud, which is the codomain W, or the output vector space. That's the picture, the conceptual picture that maybe you should have with respect to range. In a generic sense, it doesn't have to fill all of the output vector space. And this is what we could write in sort of a set notation, that the range of T is this set of vectors W in the output space that are generated by all possible vectors from our input vector space V. You give me any input vector little v, if I map it through T, that will give me a vector in my output in my range of T. And if we wanted to say that in words, then the range of T is all the possible outputs from that map in W. So the range obviously depends on the map T. This is a movie today, isn't it? I had writer's cramp, so I just decided to write it all before class. And I'll just read it. No, I'm going to start writing in just a minute. But one thing to remember is that the null space of T is a subspace. And we have the similar notion or concept for the range space. The range space is also a subspace, which is nice. That means what? It contains the zero vector, doesn't it? The range space. It also, if you give me two vectors in that range space, I can combine them linearly, and that result is going to be in the range space. Also, if I take a vector in the range space and I scale it, that scaled version will also be in the range space. So the range, this is proposition 319, the range is a subspace. Or writing that out now is that the range of T, now I'll try to write a script R. Script R of T is a subspace in the output vector space W. And I'm not going to walk through that proof. That's in the book, and we kind of talked about it. It has to satisfy three properties. So I'll just say C. Axler for the proof. Now let's talk about this counterpart to injective maps that I promised in the list of topics for today, and that's this surjective map. And again, I'm focusing on R because this surjective map has a connection with the range space. And if you don't like the term surjective, which doesn't really resonate with me that much, you can also think of this as an onto map. And here's the description of that. A map T, and I'm assuming that's, well, which is linear between V and W, is surjective if the range of that map, T, equals W. It fills the entire cloud. It fills the entire vector space, W. And that's why it's called an onto map. It's onto every vector in the output vector space. Or you could say every vector in the output vector space W is a possible output of the linear map T. And if you wanted to maybe have a graphical picture of that, in sort of a one-dimensional domain sense, then maybe we could think of something like that. So here, this is f of x, and this is x. So you give me any x, I can actually generate any value, real number in this picture on the vertical axis, in the vertical direction or dimension. So here's our domain, and here is our codomain. That's just a simple illustration of this relationship that is needed for a map to be surjective. Is that map injective? No, because a horizontal line can cut across that in more than one place. So we can have one without the other, and we could have both, we could have neither. A surjective map and we'll say is T, means that every vector in our output vector space W is a possible output of T. So I may be repeating myself, but I'm just hoping that at some point one of those wordings sort of makes sense to you. Now, one thing to keep in mind is the following. Whether a map is surjective or not depends on how we've defined the input vector space and the output vector space. Or whether a linear map is surjective or not depends on the input vector space and the output vector space. And that might be easier to sort of think about if I give you an example. Suppose we think about the derivative map, where T1 is now, well, here let me just say T1 is our first example, and T1 is the derivative map. That's a linear map. Let's say that that is the linear map between m-dimensional polynomials over the field of reals. That's the input vector space, and the output vector space is that same vector space. So T1 of P is the derivative of P, where P lives in this vector space of polynomials of dimension m. And here's my question. Question 1. T1, and those are the possible answers, is or is not surjective for a fixed m. So think about that. Now I have a derivative map, and I have m-dimensional polynomials. And now I want to know if that linear map is surjective or not. So if you think it is, you're going to show me a thumb that's pointed upward, close to your chest, when I count to 3. Because I don't want you doing this. Then everybody knows what your answer is, and maybe you'll influence their answer. So now we need to go into our voting booth. And these won't be papered ballots. These will be paperless ballots. It just involves your thumb. This means is not. Is that clear? Everybody ready to vote on the count of 3? T is or is not surjective for a fixed m. 1, 2, 3. Okay, I see mostly down. Why do you think it's so? That's appropriate, I guess. This is the one that's down. That's what people are voting. Why? Why is it not surjective? Let's say m was 2. So now I have x squared plus 3x plus 1. I differentiate that. What do I end up with? A polynomial. The x squared goes away, doesn't it? And I'm only left with first order powers of x or less. So I can't ever get to a second order polynomial after going through that linear map. Is that true? So you were thinking of a constant. Oh, m equal to 0? Why restrict attention to m equals 0? So m can be a finite number, finite constant. Okay, here's map 2. Map 2 is also a derivative map. And I have a similar question for question 2, or as question 2. T sub 2 is or is not surjective for a fixed m. This one I won't give you as much time to think about. So now we're mapping from an P sub m into a P sub m minus 1. 1, 2, 3. Okay, now I'm seeing a lot of thumbs up. Do you understand why that's a surjective map? You can pick any vector v you want in the input vector space, and that will allow you to get to anywhere in this m-1 polynomial vector space. Is that clear? And what's the distinction between the first example or the first map and the second? The output vector space. So whether or not a map is surjective obviously depends on the input vector space and or the output vector space. That was the point I was trying to make with those two examples. So if you wanted to think in terms of a picture, here's the domain, here's the codomain. Now if we map through T, I don't have an inner cloud within that output vector space cloud, do I? It's supposed to be, if it's surjective, if the map is surjective, I can get to any point in that output vector space. In this case, the range of T is all of W. Now we had a simple picture of a function that was surjective. What about a function that's neither injective nor surjective? Again, I'm just going to use a one-dimensional or a domain that's one-dimensional. And in this case, what I'm going to do, I'm not going to do much of anything, am I going to? Hopefully that's believable. This is now f of x equal to x squared. And w are the real numbers in the vertical direction. Or w1 is now the set x squared such that x belongs to the set of reals, or the real vector space. Why is this not injective? It fails our horizontal test, doesn't it? If I ran a horizontal test, all I have to do is find one horizontal, but I can find many where that'll cross through this function more than once. So this fails the horizontal line test. Which f of minus 2 is equal to f of 2, which is equal to 4. And obviously I hope that you can see that 2 and minus 2 are not the same. And so this one is not a 1-to-1 map. It's actually a 2-to-1 map, isn't it? except at the origin. Why is it not surjective? If I could draw that a little better, that blue curve shouldn't be anywhere below the horizontal line, should it? I can't assume any negative values as an output. And if it's surjective, I'm supposed to be able to get to any real number, and I can't with this function. It's not surjective, or the output does not produce negative numbers, since f of x is equal to x squared, and that's always non-negative, no matter what or how we select x from the vector space of reals. And for that reason, this one is not an onto map. Was that a linear map? No. Is that why it wasn't surjective and injective? No. We can find a linear map that is the same or similar, right? That's not injective and not and non-surjective. Question?
Yeah, if you redefine the output to be positive real values, could it be onto?
So now if we had a output space that was the positive reals, is that a vector space? So that one doesn't allow for scalar multiplication, does it? So yes, if we restricted to a subset, but these maps are linear maps, so we want them to be working with one vector space into another. So let's look at a linear map example that is non-injective and non-surjective. And this is going to be, what did we call that map? Generically. Dimension changing map. It changes dimensions. Goes from R3 to R5. And in fact, this is one that we had before, I believe. Suppose now the input vector we label as xyz for the three coordinates in R3. And let's let the output vector, which is living in R5, be minus x plus y minus 3z minus x plus 2y minus 4z, x plus y plus z, 2x plus 3y plus z, and x plus 2z. Now, what's the range of that linear map? You could write that down, right? W is equal to TV. So what W's can you find? Or maybe I would say, can you give me some vectors that span the range of T? And if that's the case, how many vectors would you look at initially? Well, to be the span, they have to be 5 coordinates tall, don't they? They have to be in R5 to even be considered. But now, how might we create a list of vectors that would quickly tell us, oh, any combination of this list from this list will be in the range of this linear map? Does it make sense what I'm trying to ask? How many free variables do we have in this output vector space? X, Y, and Z. So we have 3 free variables. We can manipulate those 3 independently. We can wiggle X, we can wiggle Y, and we can wiggle Z, all independently. So if we simply said, well, let's wiggle X to start with, well, that gives us a vector of -1, -1, 1, 2, 1. That's proportional to that combination of 5 coordinates. Yes? If we just wiggle X and set Y and Z to 0, then if we just wiggle X around, we'll be on this line in this 5-dimensional space. If we think the same way with Y, what if we just wiggle Y? Now we get a vector 1, 2, 1, 3, 0. And now we can do any linear combination of those 2 we want. But do you see how I'm going to get the third vector? And how many more vectors am I going to get to start with, to sort of start my spanning list? That's all I can produce, isn't it, is 3. Because I have 3 independently adjustable parameters. The last one will be -3, -4, 1, 1, and 2. And you could, if you wanted to, say, oh, there's W1, W2, and W3, if you wanted to. And this is actually now what we can call a spanning list. Everybody clear where that came from? Yes? So now do we need to check if these are linearly independent? If I'm telling you, give me a list of vectors that will produce the range space, I haven't yet specified to make it linearly independent, have I? So that's why I called this a spanning list, not a list that spans, or a linearly independent list. There may be some dependency among these 3 vectors. We haven't checked that yet, but this was the quick and dirty way to try to find all the possible vectors in our spanning list based on how we parameterized the original vector in terms of X, Y, and Z. Is that clear? So your question is valid, but we didn't go quite that far. We didn't specify it quite that specifically. Yes?
So is that statement saying the transform span, that span is the transform, or is that the span of the range?
So this, the question was, and I apologize if I didn't repeat the previous question, but the previous question was, is this spanning list guaranteed to be linearly independent? I paraphrased maybe. Or are we concerned if that's linearly independent or not? And right now I said no, we didn't voice that specific question. Now let me see if I understand what, repeat your question.
So I was asking, is that statement saying that that span spans the transform or spans the range?
So this, I should have said, if my pen works, this is the range of T. So this spanning list does equal the range of t. Any linear combination of these three vectors will give me where I can get to in the output vector space. And you could have said that that range space could have been produced by what set of vectors for my input space. How did I sort of pick W1, W2, and W3? That would have been like a standard basis in R3, wouldn't it? Because I picked X to be 1, I picked Y to be 1, and I picked Z to be 1. So you could have said, oh, you just created those W's from a standard basis from your original input vector space, where this is now what was corresponding to x equal 1, and by default all the others are 0, y equal 1, and z equal 1. And these are in fact independent vectors in V. Now, if you're observant, maybe you can actually see that these aren't linearly independent, these three vectors. There's some linear dependency among them. So if we look at this, in fact, the range of t is the span of 1, 0, minus 3, minus 7, minus 2, and 0, 1, 2, 5, 1. This is actually, if you looked at the W's, this is minus W2 minus 2W1, and this column can be created from W1 and W2. W3 is missing from those. So in fact, you can take two W1s, subtract a W2 and subtract a W3 and produce the 0 vector. And what does that tell you about those three vectors, W1, W2, and W3? They're linearly dependent, aren't they? The only way that W1, W2, and W3 could be linearly independent is if when we combine them to get the 0 vector, all the coefficients are 0. That forces all the coefficients to 0. And this is not the case. I can produce the 0 vector by a linear combination of W1, W2, and W3. Or if this doesn't look very clean, you could say, well, just take two W1s, and that's going to equal the sum of W2 and W3. That's maybe easier to look at. You can now go up here and add W2 and W3 and see that that's twice W1. That's maybe easier than trying to look at all three combined to give you the 0 vector. But now if our span of the range space of T has two vectors in it, what's the dimension of the range of T? What's the dimension of the range of T? 2. And that's obviously less than the dimension of the output vector space, W, which is the dimension of R5. And how big is that? 5. So in order for this map to be surjective, what would we have needed? How big would we have needed our range space to be in dimension? It has to be the same as the dimension of W. It had to be 5. And 2 is not equal to 5 the last time I checked. So the range of T is not all of W, so this is not a surjective map. So range of T does not span all of R5. And because of that, therefore T is not a surjective map. And this was our map from before, and before we were talking about null spaces in the previous time together. And there I think we showed that T had a non-trivial null space. T is not injective either. Recall. So now I'm defaulting to your memory. Recall that the null space of T, how big should this vector be? It's going to be a vector, tall and thin. How tall is it? How many coordinates or elements tall is it? 3. It has to be the size of our input vector space. So now we're stacking 3 elements on top of each other. And those, I think, from last time, minus 2, 1, 1, any linear combination in that line in 3 space would map you where? To the 0 vector. So in this case, the null space of T, is it all of R3? How many vectors are in that null space? Just 1. So it has a dimension of 1, and we need a dimension of what to be R3? 3. So this null space is a subspace or a subset. It's actually a subspace since it's the null space of R3. The dimension of the null space of T is equal to 1, and a one-dimensional line, or that's a one-dimensional line through the origin in R3. Or maybe I should say the origin in (3D) space. So now T is not injective, or T, or I should, let me say it another way, the null space of T is non-trivial. If the null space of T is trivial, that means it's just the 0 vector. But it was more than that. It was this one-dimensional line proportional to minus 2, 1, 1 in 3 space. I know you want to sort of go home and play with all of these, so let me just show you one way that you can start playing with these concepts, right? I know you're just waiting to do that, to get home to do that, right? I know you want to stay in the classroom a long time, but if you do go home, you want to just pick it back where you left it, right? So now, illustration of t being non-injective. Suppose I pick a u1 equaling minus 2, 1, 1. What happens when I map it through this linear map that we've been playing with? That's the 0 vector in R5. So now what if I give you a different vector? Suppose I give you v1 equaling 1, 0, 0. So that won't be too hard to go and plug in to that. Now we just need to set the x's to 1. Y and z are both 0. And now with only the x's pulled off from t, we should end up with, I hope, minus 1, 1, 2, and 1. So that's where we get to in R5 from v1. But what if I form a new vector, v2, which is a linear combination of v1 and u1? v1 was 1, 0, 0. u1 was minus 2, 1, 1. Or now I'm at minus 1, 1, 1. And if I now use that as an input to this linear map, you could brute force go through and put x equal to minus 1, y equal to 1, and z equal to 1, and find out what you generate. And if we do that, so we just negate the x ones, which is 1, 1, minus 1, minus 2, minus 1. We pull in just the y's, and that's 1, 2, 1, 3, and nothing. And then we pull in just the z's, which is minus 3, minus 4, plus 1, and plus 2. And if we do our algebra, what do we have in the top element? Minus 1, minus 1, minus 1, negative minus 1. Just making sure. Then we have a 2 and a 1. Does that look familiar? It should, because we really could have used what? Additivity, and said this is TV1 plus TU1, and TU1 is nothing, and TV1 is what I just wrote down. But what have we shown? We've shown, or this illustration now shows that t applied to v1, which is minus 1, 1, 2, 1, is the same as t of v2, but v1 does not equal v sub 2. And it would have to be if t was injective, if t was 1 to 1. Then if we get to the same point in the output space, we should have come from the same beginning vector in the input space. Now I'm curious from this example if anyone sort of saw anything popping out at them that might be interesting. And everybody should just have their eyes wide open, just all excited, saying, yeah, I saw this. I observed that. Yeah. See? Okay. Humor me a little, please. Dimension of V. What is that? What's the dimension of our... So here is... This is the input vector space. And I'm asking for the dimension of that, or I'm asking for the dimension of the domain. That should be the same as the dimension of R3, since that's what V is. And you know what that is. That's x, y, z. What's the dimension of this three-dimensional space? 3. But now let's look at that relative to the dimension of the null space of T and the dimension of the range of T. From that example, how big was the null space of T's dimension? That was one line. How big was the range of T? 2. Coincidence? I mean, the dimension, the range of T is where? What vector space? W. The output. What's the null space of T? V. Oh, why would those happen to be adding up to the dimension of the input vector space? Must be a coincidence? No, it's not. So that leads us to, and this is how you might create a new theorem. You might stumble across a relationship like this and go, let me try another linear map. Generic linear map. Wow, the same thing happens. Let me try to find a counterexample. Let me try another one. You try another one. Get this same result. Maybe this is a true statement. So now you need to prove that, or say, let me just assume that's a valid theorem or a valid proposition. If so, let me prove it. In fact, it is a proposition. So that, well, actually, it's labeled a theorem, which means it's even more powerful than a proposition. So now we have a theorem, 322, and it's labeled as, or titled as, the fundamental theorem of linear maps. That sounds kind of important, doesn't it? More than just a coincidence. So now this theorem, 22 in chapter 3, says given a V, or given V, let me say it this way, given V, a finite dimensional vector space, and in fact I might get tired of writing all of that, and you might too if you're texting this to mom or dad, so you might just say FDVS and they'll know exactly what you're talking about. They'll Google it and they'll find, maybe not, maybe you better not do that. I don't know what it'll come up on Google, but FDVS for us stands for finite dimensional vector space. So now you're given V, a finite dimensional vector space, and a linear map. t that's mapping between the input vector space v and an output vector space w. Then the range of t is a finite dimensional subspace of W, and we end up with the dimension of V equaling the dimension of the null space of T plus the dimension of the range space of T. Where this is the dimension of domain, which is our input vector space. The null space of T is a subspace of our input vector space V, and the range of T is a subspace of the output vector space. So let's see if we can show why this is true. Or let's prove this theorem. So hopefully you've had your coffee, because this is going to get a little bit, well, you have to kind of pay attention. So first let's just assume the dimension of the null space of T. And let's assume that that's m in size. So we just are arbitrarily saying, let's let the dimension of the null space of T be m. If that's the case, how can we build a set of bases, or how can we build a basis for that null space? Or if I now make a list of basis vectors and I call them U sub, U1, U2, how many are going to be in that basis list? M. So now we have M such U's. Now from Theorem 33 in Chapter 2, what can we do if M is less than the total dimension of our input vector space? So this is a basis of a subspace of the input vector space. We can now do what to maybe get a basis for the input vector space based on Theorem 233? I know you have all of these theorems memorized. You can add vectors, can't you? You can now extend this list to form a basis on V. So from Theorem 233, we know we can extend this basis of the null space of T on the null space of T to a basis of the input vector space V by adding vectors as necessary. So we can just start adding vectors to this that are what? Linearly independent of these U's, and they're helping span all of V. That's what a basis does. The U's are linearly independent and they span the null space of T. But now we're going to introduce some new vectors, and we'll call those W's to fill all of V. And let's now just establish notation. Suppose we let U1, U2 through U sub m be m of those vectors, and then let's complete the basis of V by adding in W1, W2 up through Wn. What's now the dimension of V? M plus n. And now what we need to do to complete the proof, M is the dimension of our null space. We now need to show that the dimension of the range space of T equals n. So let me just state that. To complete the proof, we must show that the dimension of the range of T is n, where the range of T is a subspace of W. Let's pick a vector from our input vector space V. And this is now any generic vector, and how can we write that in terms of our basis vectors? Some linear combination of U's and W's. So let's say V is A1 U1 plus A sub 2 U2 up to A sub m U sub m plus B1 W1 plus B sub 2 W2 B sub n W sub n. What happens when we map V through this linear map T? What happens with, so now V, now we're using additivity, aren't we? Or thinking about using additivity. And now we can map A1 U1 through T, A2 U2 through T. What happens when we map those U's through T? They're in the null space, so they map to 0. So we are left then with B1 T W1. Because of the null space property on the U's, but now we're using homogeneity on the W's. So I'm sliding that B1, or the coefficient, outside of the linear map. Is that okay? So this is now plus B sub 2 T W2 plus B sub n T Wn. And if you're following along and you want to remember where this came from, using the fact that T of U sub j is equal to 0 for all j in 0 through m. Why did I say 0? I didn't. I started with u1, didn't I? So now from 1 to m, because u sub j's are basis vectors in the null space of T. Now let's look at what V is. Notice that since V, we didn't pick a particular one, we just said give me a V, a generic V. So notice that since V was arbitrary, then we can think of two different outcomes. TV will span what? Now we're picking arbitrary vectors from our input vector space. This is now going to fill the range, isn't it, of T. So now TV will span the range of T. And any TV can be expressed as a linear combination of these TWJs based on that outcome. Thus, the list of vectors TW1, TW2, TWN spans the range of T. Or the range of T is the span of T WJs. So what we need to do now, so to complete the proof, we need to show that this spanning list of TWJs is linearly independent, and if that's the case, that allows us to say that its dimension is little n. If there was some linear dependencies in there, then all bets are off. We couldn't say anything really about little n. But if we can show that this spanning list consists of linearly independent vectors, then we can say, oh, we have n of those. And that's really what we're after. So that the dimension of the range of T is n. So let's now consider a linear combination of those vectors. Now consider a linear combination of TWJ such that C1 TW1 plus C sub 2 TW2 C sub n TWN is equal to 0. So now we have vectors. Let's combine them, linearly combine them to get the 0 vector. What can we say about that sum based on the homogeneity property? We can put those constants back inside the argument of t, can't we? So now we can say t operating on C1W1 plus C2W2 plus C sub n Wn is equal to 0. And now what can we say about that vector that's the argument of t, and it's getting mapped to the 0 vector? Thus, C1W1 plus C2W2 this vector, where does it belong or live? That's in the null space of T, since it gives us the 0 vector. And if that's the case, we already have a basis for the null space. So now we can write this vector as a linear combination of basis vectors. I told you you need your coffee, of our basis on the null space. So we can expand or build this vector or represent this vector in terms of U sub L's, since that vector linear sum of W's lies in the null space of T. So that says C1W1 plus C2W2 up to C sub n Wn is equal to, let's say, D1U1 plus D2U2 up to D sub m U sub m. But what do we know about all of these vectors in that equation, the W's and the U's? How did we create those W's? We had U1, U2, U sub m to begin with to form a basis of the null space of T. Then we did what? We expanded that to get a basis for the input space by creating these W's. And what do we know then if that set of vectors forms a basis? What do we know about those vectors? Those are linearly independent. These are linearly independent by construction. And if you'll give me one more minute, I apologize, but we're almost there, and I really hate not to finish this up. But I think you see where we're going, right? Or do you want me to just finish it up offline? Now what do we know? If those are linearly independent by construction, those W's and U's, what do we know has to be true in that equation? All those coefficients have to be 0, don't they? The C's are all 0 and the D's are all 0. And if the C's are all 0, then what do we know about this equation? Then all these TW1, TW2, TWN are linearly independent. And that's what we were after. And how many of those vectors do we have? N. And that's what we wanted to show. We wanted to show that they spanned the range of T and they were linearly independent, and for that reason it gave us the dimension of the range space of T. So I'll write that up, but I think word-wise we're okay to be calling it finished. We'll stick a fork in it. We'll be done. We'll pick up with some corollaries maybe, stating those the next time we meet.